Offered by who?
Offered by the geography.
Okay, thanks. Today I'm officially old, so okay. So welcome back. Before I start today, and we close today the quadruple part with the expression for the gravitational wave amplitude. I just want to tell you two things. So there will be, like I probably mentioned at the beginning of the lectures, we're gonna put a link to a Git folder on the website, and you can find like the exercises and notebooks that Costantino um, cast yesterday. I'll also give a very a PDF with an exercise and some and a Mathematica notebook, an exercise that will complement a bit the very last, I mean, the very first 20 minutes that we'll do today on computing like like a real gravitational wave event. It would be nice if you can try to do this. I mean, it's a very simple exercise that actually is mutuated or taken from the Physics and Mathematics Olympic Games that I helped to organize when I was postdoc in Lisbon. And so it's a very nice exercise that shows you how to use the data to compute like some parameters relative to the binary evolution. It would be nice if you could do this, and like maybe we can discuss during the office hours, or I mean in the remaining like 3 days. And the last thing that I want to ask you, how many of you have installed on the laptop, or at least have seen Mathematica? Raise hands. Ah, okay. Almost everyone, because I was thinking like the last hour we can actually do an hands-on. So the plan, just to tell you, is that we complete the binary part, then we start discussing tidal interaction. I'm gonna present the way that we compute these love numbers that I mentioned, and also the background solution. So how basically you derive what are called like the Tolman-Oppenheimer-Volkov equation. I don't know if you heard about that. But I'm gonna give on the Git repository some Mathematica notebook to derive this equation, starting step by step from the Einstein equation, and then some numerical routines that I created to build the stars and compute love numbers. But maybe it would be nice if the last hour, for example, we can do this together, so I can show you how to do it, and we can integrate numerically, so you can have like some tools that you can use and to play with. If someone doesn't have Mathematica, or has never seen it, you can maybe gather in groups, and we can do this as a social activity. Okay. All right. So for the rest, yes, let me make a summary what we seen yesterday. So we have seen that the we have seen this basically, that the gravitational wave amplitude basically has this form here. These are the components that solves the Einstein equation at the perturbative level at the first order, and that they are proportional to this quadruple Q of n, K of t, which was our integral over t00 xn xk over the volume of the source. And we have applied this to the binary system. So you have your binary with L0, which was the orbital distance. And what we seen yesterday at the very end is that you take this binary on a constant orbit, but then if you allow, as they do, like gravitational wave emission, the orbit basically shrinks. So basically the two objects get closer and closer. And the last results that we show yesterday was that this L0 gets promoted to a time-dependent quantity, which is can be computed at the leading order in the gravitational wave emission in this way. Okay, so L0 of t from a starting value L0, whatever it is, decrease over time, and actually goes to 0 as t call, and this for us was the coalescence time. Okay, now these can be used to understand what happens to our Keplerian frequency that now as well becomes time dependent. And this is because our original Gm over L0 3 becomes L0 T3. And if you plug in immediately that equation there, you find that this can be written as this, where of course your omega k initial is the Gm L0 3 initial power of 3. Okay, so L0 decreases in time, so omega k increases in time. And as you see, actually, since L0 goes to 0 for t that approaches t coalescence, you would expect that the frequency blows up and actually diverges. Okay? So of course this doesn't happen in reality, in the sense that the frequency then never goes to infinity. It's just that this approximation behaves very, very poorly as you get closer to the merger, where all our assumption of the slow velocity, weak field approximation do not hold. Okay? So if you want to do this and you want to become more and more accurate and have like a more faithful description as you go toward the merger, you can basically do two things. You can work out calculation analytically, and as I was telling you, basically you can compute, if you wish, the omega t with the piece that we have computed, which is the quadrupole approximation, plus what are called post-Newtonian terms. And these post-Newtonian terms are basically an expansion in powers of V over C. Okay, you can basically do the same thing that we've done, but adding more term in the perturbation and taking care of adding basically relativistic correction to your quadrupole formula. And you can get indeed a basically semi-analytic expression for the evolution of the orbital phase and the gravitational phase, and also of the amplitude of the gravitational waves, that will provide you a more reliable description of the spiral, but this description in any case will inevitably fail when you go closer to the merger. When you're very, very close to the mergers, there's no other way that solve basically the Einstein equation numerically, literally like on a grid. So basically this means using numerical relativity, because then the nonlinear character becomes so prominent that there's no, you cannot work out any reliable analytic approximation, okay? But of course, up to a certain point, I'll come back later in when I show some slide later on, but up to a certain point, you can improve this analytic description that we are developing during this course. Okay, we have this, and last time we said that the gravitational wave frequency was twice the Keplerian frequency. So in our case, basically this is 2 omega k divided by 2 pi. So the gravitational wave frequency is immediately related to the Keplerian. Okay, now the last piece to have everything on the same foot are two things. The first is, if you remember, we defined like yesterday the gravitational wave, the component of h mu nu as this guy here contains cos for a binary, cos and sine of the orbital frequency depending on time, and then there was a factor outside, you can look at your note, which was the amplitude. And that amplitude depends on the masses of the binary and on the frequency. Now for us, this H0 will be, I'll just give you the final formula, but what you have just to do is replace the values of Ni gravitational wave depending on time on that formula. What you find that the final expression will be this. Now, if you look on your notebook, there are two differences with respect to the formula that we have written yesterday. The first one we have discussed yesterday, so that we have replaced the frequency of gravitational wave with something that depends on time. And then that I have rearranged the masses that you see, introducing a new variable. So before, there was basically a product with some powers of the total mass and the reduced mass. But you can cast those two parameters in terms of a single parameter, mass parameter, which is called the chirp mass. So this curly m, which is the chirp mass, is equal to H0. So it's, if you take your notes of yesterday, we basically wrote the components Hij as minus H0 and then Aij Tt. This was in the Tt gauge. Okay, so basically the Hij was a matrix containing cos omega k t blah blah blah, and then H0 just contains the 1 over R dependence and the mass products. Okay, if you look at, and within this H0 that we wrote yesterday, there was a combination of masses that now we have rewritten this combination of masses of the total mass and of the reduced mass that we have rewritten in terms of a new mass variable, which is the chirp mass. So the amplitude of the gravitational wave depends on the chirp mass and on a frequency, on a time-dependent frequency. Yeah, this is the gravitational wave frequencies, yes. I don't have the notes with me, but basically this was the factor. So this H0 just, so there was a factor like with some powers of G, 1 over R, some other powers of, and I just called everything of this as H0. So all the constant terms, okay, all the constant terms that weren't depending basically on the cosine and sine of the angular frequency, okay. Now, this tells you something, besides recasting everything in terms of the chirp mass, and the fact that it's called chirp has a physical, actually has a meaning. There's a reason why it's called chirp. As you see from H0 and gravitational wave and the gravitational wave, both the frequency and the amplitude grow in time. So, yes. Yeah, what is it? Well, yeah, if you wish, yes. Well, I'll come in a second. And indeed, this is actually one of the exercises that you're gonna, one of the exercises that I was telling you that it would be nice if you can do is actually how to use the dependence on the gravitational wave on the masses to measure the masses. So you get from the data these, and then you go back to the masses. So the frequency and the amplitude both grows in time, okay? And this is basically, the name chirp comes because if you characterize like the chirping of a bird, it works exactly in the same way. So the birds sing such that the frequency of their singing and the amplitude of the singing increases in time. And so this is why it's called chirp mass. But there is also another very peculiar aspect, is that, so you can measure, so when you get the gravitational wave, you can make measurements of both the amplitude and the phase of the signal, which is encoded there, and the phase will carry some extra information, but on the property of the binaries. But as you see here, the leading contribution in terms of the mass is given by the Chirp mass, in the sense that from a disorder, okay, when you want to make a measurement, so you want to extract from the data the parameters of the binary, you won't be able to separate singularly the M1, M2. What you can get is just a combination of the two. And this is why if you open all the parameters, all the LIGO papers, LIGO and Virgo papers, you're going to see that the best measured parameter is always the chirp mass, because this is the parameter that enters at the leading order here, enters at the leading order here, and as I will show, enters at the leading order even in the phase of the gravitational wave here. So if you want, with the quadruple approximation, you cannot measure really the single masses independently. You only measure a combination of the two. How do you measure like the two masses? Because if you develop the post-Newtonian approximation that I was telling you, at the next to leading order, there are other combination of masses. For example, together with the chirp mass, you get another combination, which is the symmetric mass ratio, which is m1, m2 divided by m squared. So you need both those terms to measure. At that point, you have like two unknown variables, like the chirp mass and the symmetric mass ratio, that you measure from the data, and then you can solve them back to get m1, m2 independently. Okay, but at the leading order, the only things that you can measure is this. And this is indeed the most accurate parameters. If you look, for example, at the LIGO paper, you're gonna get that the chirp mass is measured with the gravitation, the GV170817, so the baryon neutron star merger, as like a chirp mass measured with an accuracy of, I think, below %. All the other parameters are have way larger accuracy. And if you look at the paper, you can find a measurement, a constraint on the chirp mass and a constraint on the single masses. But the constraint on the single masses is always way looser than the one on the single parameters, and in particular on the chirp mass. Okay, so this is why the fact that if you open the papers and you see that this is the parameter that is most measured with the tightest accuracy, it is because it's the term that dominates the amplitude and also the phase of the gravitational wave. All other parameters enter at subdominant order. And indeed, we can actually see now also how the phase depends on time. Because now instead of omega k t, which was our phi, we need to replace everything as an integrated phase because omega k depends on time. So instead of this was our phi, now we need to define a phi of t, which is the integral over t of 2 omega k t prime dt prime. So because omega now depends on time, you have to integrate in order to get this phi of t. And this is the integral 2 pi ni gravitational wave t prime in dt prime. I don't need this. And yeah, let me write these last two results here. Which I think close really the circle. So if you then, you can make this integral analytically, because you know we have written somewhere, probably I cancel it, but we have written the explicit expression of ni, gravitational wave, as a function of time. So you can perform this integral analytically, and at the end what you get is this, that phi of t becomes of an initial phase minus 2. I hope that I Let me write it down. And also, as your colleague was suggesting, let me also write the expression, the final expression of the gravitational wave frequency, but in terms of the chirp mass. Okay, so I think that this is the final message of these 2 hours and 20 minutes of lectures, okay? I think if you want to make a summary of what we have discussed so far, is the following, that the perturbation on top of the flat background obey to a wave equation. They propagate at the speed of light, they are transverse. So the polarization tensor is orthogonal to the direction of propagation. They can be expressed in terms of the source quadrupole. Which also tells us that gravitational waves need degrees of asymmetry because their origin is of quadrupolar nature, unlike electromagnetic waves, which are dipolar waves by construction. And working out the calculation for the binary system, we have seen that if you know the amplitude and the phase of the detector, in general, with the detector, what you really measure is the phase and its time derivative, so the frequency. This is the best thing that you can measure. The amplitude. Gravitational wave detectors are not I mean, they measure it, but I mean, the thing that they measure with the tightest accuracy is the phase and the frequency evolution rather than the amplitude. This is just because how they are built. And but in principle, if you measure like phi t, nu gravitational waves and h naught, you can infer the binary, you can constrain the binary parameters. And the parameter that is constrained with the tightest accuracy is the chirp mass, just because basically it's the only mass parameter that enters in all the observables that you see there. So both the amplitude and the phase frequencies depends on the leading order on the chirp mass. Okay, if you want to measure other parameters, you need to go at the next to leading order. And indeed, let me go back just to show. This was the slide that I showed the first lecture. So in these 2 hours, in 2 hours and something, what we have computed is that one. So as if you see here, this is the post-Newtonian approximation. So when I wrote at the blackboard that we had like the quadrupolar plus post-Newtonian term, we have worked out the quadrupolar approximation. So in front of the psi point particle there is a common factor which depends on the chirp mass, okay? And then we have basically computed that factor there. If you go computing other terms, and when I say other terms means corrections in powers of 1 over c, you see that there are other contributions coming to the waveforms, and this contribution depend on the source parameter, and in particular on that eta that I was mentioning, that is m1, m2 divided by m. Okay? And of course, there are different parameters. I think that the spins, if I remember correctly, enter at the leading order at the 1 over C23, so they are like or 2, like let's say 1.5 pn contribution. This is where the spin comes. So they come at a next to next leading order to the masses. So you can basically create a hierarchy of parameters measured with less and less tight accuracy. And then, I mean, if you go all up to the 5 pn term, 5 post-Newtonian term, so what is a V over 10 divided by C over 10, you then meet the tidal contribution, so the tidal log number. And this is why at the beginning of the lectures, I was telling you, I mean, this is a very small term in principle, and given that there is this hierarchy for which we measure the chirp mass with the best accuracy, then when you add more parameter, all these parameters get measured with less and less accuracy, and so you would expect this lambda to be very subdominant with because of the order here, and also coming at such high order that you don't get a very good measurement of it. And indeed, it's difficult to measure it, but considering that this in principle is a big number, as we're gonna see, it actually gets boosted in the waveform. And indeed, we measured it for the first binary neutron star event, and in particular, this combination was at very high confidence level, the measurement of that parameter lambda there excluded 0, which means that there was some matter, because that lambda is different from 0 only if there is matter around. So basically excluding 0, the first the gravitational wave observation of the binary neutron star basically confirmed that we were looking at something that was not vacuum, but there was basically 2 stars going around there. Okay? Yeah. No, you have also point particle contribution that nobody has computed. There is to be honest, I never really understood, but I mean, there is a way to port, to make not a reasonable guess, but I mean, there is a series of answers that allows to identify where tidal effects enters at the leading order, and they tell you that it enters at the 5 pn order, and there's a way to construct them, and it's where they start. For point particle, in principle, you have to, there's no this recipe, so you have to follow all the way, so you need first the 4 pn and then the 5 pn, and I think that not even the 4 pn are all, because to compute the 4 pn, to compute each term there, you need the binding energy and the fluxes, both of them, as we said, basically and I think at the moment there is only the binding energy known at the 4th order, so they are computing, I mean, it's also not clear whether it's always, as Leonardo says, I mean, it's always nice to have an analytical approximation, and because, I mean, you have more control of the things, but these are also terms which are very high in the frequency and close to the merger, where numerical relativity is effective, works. So you may also think that instead of computing all these super difficult calculate, which may actually be impossible to compute analytically, in the sense that I was talking with a friend of mine that does post-Newtonian calculation, and at the moment it's not only that calculations are complex, that there are some integrals that they don't know literally how to solve. But one way, the way that we construct the waveforms is that we have this post-Newtonian expansion that models the spiral, and then you stick numerical relativity simulations. Now, numerical relativity simulation, basically, if you look at the waveform, sorry, I mean, I'm very, very bad in, this should be a waveform, but this is the merger phase, okay, and this is the spiral phase, okay. Now, numerical relativity is very expensive computationally, so you cannot do, they can do like, I don't know, order of 10 orbits, okay, before the merger. So this is the merger, and they can do a very limited amount of orbits, because going at lower and lower frequency and modeling more orbits just require too much computational power, okay? Just matter of, you need resolution, you need CPUs, I mean, at some point it becomes also not very eco-friendly. I mean, because we are burning a lot of electricity for gravitational waves. I mean, there are better options to use energy. So the basic idea that which we compute templates use basically hybrid waveforms. So we know that the post-Newtonian approximation, that thing works very well up to a certain point. We know that that breaks at some point, but the numerical relativity works. So we stick the two things together at some particular frequency, such then that you have a semi-analytic waveform that covers everything, which is an hybrid between fully numerical and fully analytical. Okay, so you may think at that point, especially because I mean the numerical relativity are becoming more efficient, that it's not really worth to go. Oh, if you talk with post-Newtonian people, they always say that it's worth going. But I mean, for a practical level, I mean, maybe it's not really worth, and you can just rely on these things and just stick them together. Okay. Just to tell you that this is the super famous plot that I guess that all of you have seen, because when we yesterday, I have some probably numbers, or did I forgot? Yes, yesterday. I'm sorry that Leonardo is not here, because this was an emotional lecture for him. So yesterday we computed dt in dt, so the change in the orbital period of the binary as a function of the time, and basically this was proportional to the gravitational wave luminosity, which was the way that gravitational waves were discovered indirectly, so with that thing there. So what you see there is basically the, if you wish, like the cumulative shift in the period, well, in the periastron time of the Alsen-Taylor binary. So the first binary pulsar discovered, integrated over 35 years, no, 45 years. 35 years, okay. And you see, the dots are the actual measurements, and what really strikes me always of this figure is that the continuous line is not the fit, is the prediction of general relativity. Okay, so they just match perfectly. And just to give you like some numbers for this binary, which is called as PSR 1931 plus 16, you have two masses of 1.4 solar masses. The estimated L0, so the relative distance, is of the order of 10 to, I have a precise number, 10 to 12 centimeters. Now, just as a reference, this thing here, so this is the relative difference between the two bodies, and this more or less corresponds to twice the solar radius. Okay, so just to give you like the size, typical scale, we have two neutron stars, so two objects of 10 kilometers around, which goes around, which orbits with a relative distance of twice the orbits, the sun radius. So the system is made by compact objects, and the system per se is very compact. Okay, and the gravitational waves emitted by these guys is twice the Keplerian frequency, as we see, and this is 3.6 10 to minus 5 Hertz. The predicted, of course, because this wasn't observed directly. So if you use the parameters inferred from the decay and blah, 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 you measure that it is this. And if you actually plug these numbers and you see the wavelength of gravitational waves as basically c over n gravitational wave, this is 10 to 14 centimeters, which is much larger than L0. So if you remember, we started our quadruple approximation, the derivation, blah, 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 requiring that the gravitational wave wavelength was much larger than the typical scale of your system of interest, which indeed applies in this case. So indeed, for this binary, like the quadruple approximation is enough, and this is the only thing that you need to describe the system. it's funny that they actually found more relativistic systems for which you need to include more terms in the orbital dynamics description. So you need even relativistic correction to the what are called like the post-Keplerian correction, and they allowed to measure other parameters with not only like actually to check relativistic deviations not only in the leading quadrupolar term but also in the subdominant contribution. But for this system, everything was very, very fulfilled. And indeed, this, well, okay, I think they got the Nobel Prize not for the gravitational waves, of course, but for the discovery of the first binary pulsars. So it was the first example. Of course, this, again, the point is that this is the typical frequency of these binary pulsars is the order of 10 to minus 5 Hertz, which is way larger than what we would way smaller than the typical frequency of the systems observed with LIGO and Virgo, because now you have yeah, so what is it? This is basically the system that we observe was the binary pulsar that I show you was here, and now we observe systems which are in this range of frequencies. So with periods of the order of seconds, slightly smaller here. And this is what we have basically with gravity. I'll have a slide now, but we are observing here these objects that emit gravitational waves in this frequency range. And with next generation detector, what we are doing is going a bit like opening a bit of a window also on the kilohertz. In principle, like current gravitational wave detectors can measure like signals in the kilohertz regime, but I mean they are not really accurate in the sense that if you look at the sensitivity curves, I mean it becomes a bit any constraints on the parameters becomes very, very loose because the sensitivity curve is not very good at that time. So with next ground-based detectors like the Einstein telescope or Cosmic Explorer, we should be able to open this window, so go like really in the kilohertz, really like having an effective window on the kilohertz, and most of all, going closer to the 1 hertz wall, because unfortunately, like at low hertz, let's say current detector, I think can go around 10 hertz. They cannot really go lower because there's seismic noise that you have to beat, and current detectors are not built for that. You need like to build underground on some particular design that is not installed like in LIGO and Virgo. The Einstein telescope, for example, will be underground, and it will go to let's say the wall is 1 hertz, 3 hertz, depending on the configuration. Now, going from 1 or 3 to 10 hertz, you may expect that, I mean, this is what's inside 7 hertz. There is tons of physics in 7 hertz. And because the binaries basically evolve slower and slower as the frequency is lower. So in the sense, if you have like a higher frequency, the binary will just evolve very, very fast. While if you have binaries like at 1 hertz, 2 hertz, they will be very, very slow, which basically means that like in 7 hertz, there will be hundreds of thousands of cycles compared. So the first gravitational wave event that we observed had very, very few cycles, like I think less than 10. Okay, and it lasted for milliseconds. If you take a binary neutron star, the binary neutron star that we have seen, I'm sorry that I'm recorded because I can say very stupid things, but I think that the length of the emission was around 1 minute. With the Einstein telescope, we're gonna go around 1 hours to days of observation. And this is because they will spend the majority of time in those 10 hertz. So they will basically they will evolve so slowly, emitting at the sub 10 Hz regime, they will complete tons and tons of orbits, hundreds of thousands, and so you will observe them continuously up to 1 day. Now, if you observe things for a longer time and these evolve completing instead of 2,000 of 10,000 cycles, and you are able to track those cycles, you can make parameter estimation with much more accuracy, which means not only like measuring the masses, but measuring all the properties of the spiral. So for example, like I'll go back at the very end of the lecture on this, like trying to measure deviations from GR, some the prediction, trying to see whether there's something else besides black hole or neutron star, and so on and so forth. Okay, so this very little wind of 10 hertz can actually do a lot in terms of what fundamental physics. In the space, we're actually trying to go even lower at frequency, and this needs to be done with frequency, with space detectors. And yeah, this comes from a nice tool which is called the GW plotter. It's online, and you can there are different noise curves and sources that you can plot. It's like I think it's a Python code, something that you can run online. So basically, this is the windows of current detector with a lot of current generation detectors. This is the, I think these are the current generation detector. This should be the Einstein telescope, which gains an order of magnitude with respect to current detectors. And so if you want to go at lower frequencies, so the order of 10 to 2, 10 to minus 3, you get LISA. This was the ELISA, which I think was the version of LISA when LISA was a NASA European collaboration. NASA cut the funds, and then it became ELISA, European LISA. Then they came back, and this is the thing that they are actually building now. LISA has been approved last year, so hopefully it's going to fly in 2035-7, and this is the predicted sensitivity curve. So it's going to be very, very good for measuring like things between 10 to minus 5 and 1 hertz, so way lower current detectors. And there are sources that you will never be able to observe with LIGO and Virgo, in particular like supermassive black holes. So if you take binaries with two objects of 10 to 5, 10 to 6, 10 to 7 solar masses, they emit gravitational waves that fall in the LISA band, not in the ground-based detectors. And also, something that I'm particularly attached in this period, extreme mass ratio spirals, so asymmetric binary, so something like with a component of 10 to 6 and the other component of 10 solar masses, for example. So very, very asymmetric in mass ratio. They are very peculiar sources, and they emit, if you see the signal, they really emit like here. So in the bucket of LISA, they are completely dim, obscure to ground-based detector. Then there are like some prototype, because LISA is more or less around 1 hertz, like the sensitivity curves goes up around 1 hertz. The current detectors, or even the future detector, will actually have a low frequency wall around 1 hertz. If you want something which is very sensitive in the 10 hertz, so around 0.1, so in which the curve doesn't really raise around 1 hertz, either on the low end side or on the upper end side, you need a specific detector that is targeting the 10 hertz regime, which is, for example, this one, the 10 hertz, the SIGO satellite, or there are now in development, like believe it or not, but lunar moon-based observatories. So one of these is actually developed by Jan Arms at the Grand Sasso Science Institute. So basically they're trying to install seismometers on the moon that are effective in the 10 hertz regime. If you want to go, and this is the last thing, if you want to go even at lower frequency, so the nanohertz, where you need or future detector, other satellites different from LISA, or you can use, for example, PTA. So you can track the signals emitted from pulsar. You can see variation in the signals, and you can correlate variation changes in the expected signals to the interference of gravitational waves, and this interference, to interfere with those signals, must be in the nanohertz range. Okay, so those are, I don't know how to call it, direct or indirect detectors of nanohertz gravitational wave detectors, gravitational wave signals. Nothing. Okay, I think we can make the break, and we'll come back in 5 minutes, and we'll start with tidal interactions. Okay, now if you remember the sketch of the gravitational waves, the gravitational wave signal, well, which I discussed before. So when I said, okay, we have basically spent 2 hours and 3 hours computing the one, what I want to give you now is an insight on the 5pn term, so on the tidal deformability term. And I don't want to compute the waveform. You need a PhD in post-Newtonian theory to do that. Just I want to give you a sketch, and I want to build a storyline on how we compute the law of numbers. And to compute the law of numbers, you need something which is called relativistic perturbation theory, which is actually something very, very useful that you apply, will apply to the computation of the tidal law of numbers, but you can also use in general to study the behavior of compact objects of equilibrium. And for example, you can use them to compute the quasi-normal modes of a black hole. It's the same technology cooked with a different source, but it's basically exactly the same. So I want to compute lambda. I want to show how to compute lambda and K2. Actually, I want to show you how to compute K2 and lambda. Incidentally, to compute K2, you compute K2 and lambda, so the log number and the tidal deformability, doing perturbation on a background. Okay, the background, as a background, we'll consider that of a star. So the basic game that we're going to play in the next hours will be, we'll take a neutron star, model as a spherically symmetric background. Okay, we will do relativistic perturbation of this guy, and we will show how the perturbations are related to the law of numbers. But since we are computing also the background, incidentally, I will also show you how to compute the radius of a neutron star and the mass of a neutron star for a given equation of state. This is why I told you that it would be nice the last lecture to do like a hands-on session in which I show you how to integrate the equation that we're going to derive. So you can build, if you remember, the curves that we show at the beginning of the lecture, that basically had the mass radius curves. So basically these curves corresponds to stellar configurations for a given equation of state. So the given equation of state was a relation between the pressure and the energy density of the star that you integrate, and these lines here are basically points. Each point corresponds to a particular star with a mass and a radius for a given equation of state. What I'm going to give you is a recipe to compute these, and besides M and R, compute K2 and lambda. Okay, and what we can do at the very end of the lecture is doing this together at the practical level, so solve this equation together. Numerical, I mean. But before doing this, I'm going to give you a sketch of the Newtonian tides, which is always nice. And so at the level of, because it would be more complex, and actually, to be honest, I find the relativistic description of tidal forces easier in relativity, especially in the computation of law of numbers with compared to Newtonian gravity, but okay. So I just want to, at the beginning, discuss tidal forces and which are encoded, or you can define something which is called the tidal tensor, which describe tidal forces in Newtonian gravity. And to do this, let's do as always our sketch of a two-body system in which we have like two masses, M1 and M2, with M1 which is much larger than M2. And I have some coordinates that I call capital X. With Newtonian gravity, there's no time component, everything is purely spatial components. And these X are the components of X2 in a inertial system anchored with M1. So you have a reference system anchored with M1, and the capital X define the coordinates of M2. Okay, inertial coordinate system. Okay, and then you have, let me call it small x, which are the coordinate of a third body, and small x are the coordinate with respect to M2. Such that small x plus capital X which I define as R, are the coordinate of this of the small particle with respect to m1. Okay, so this is x, capital X. This is small x, and this is R plus. Sorry, this is capital X plus small x. Okay. You see what I'm trying to do here? I basically want to study since tidal forces, what really basically measure is the relative acceleration between points in a non-uniform gravitational field. What I'm basically trying to understand here is that I'm trying to measure the gravitational force pulling on this and on this, and I'm trying to understand which is the relative acceleration between these two because of tidal forces. Okay? All right, so very, very easy. What I'm gonna assume that these objects are very close to each other, and I'm gonna just work out a couple of equations in Newtonian theory. And in particular, the Newtonian gravitational potential felt at R, so I can write this R, where my phi is just the usual gm1 over R. And since I'm assuming these two objects are very, very close to each other, I can actually make an expansion of these. And I can write this phi r capital X plus d phi dr I plus 1 over 2 the functions are evaluated and derivatives plus x cubic. So are evaluated in capital X because I'm expanding the potential here as something over x plus small deviation in x in small x. Okay, now let me use it here. What I want to study is, again, the relative acceleration between the two particles. Because this, let me write it once for all, this is small x, and because of tidal forces, what I want to understand is the relative acceleration between the two because of the tidal field. So I want to study the second derivative x small, and because I defined there, this is how I define x small, what I want to study is r dot dot minus capital X dot dot. And this is simply d phi d rk plus minus minus d phi d capital K. Now you plug those expressions inside there, you plug those expressions inside here, and you see that these at the linear order can be written as this. I won't do it, but you just have to replace that expression here, and this will cancel immediately the first derivative between the two. And the only thing that remains is this C that I actually defined capital X So this C, which is a tensor, is an object with two indices, two spatial indices, which is given by the second derivative of the Newtonian potential with respect to the coordinates. evaluate or gives the relative acceleration between these points here, okay, due to tidal forces. And indeed, it's just given by the second derivative of the Newtonian potential. You can actually define something similar in relativity, but instead of like having you can define a relativistic version of the tidal tensor, which actually involve like the Riemann tensor and like the contraction with 4 velocity and blah, blah, blah. If you take, for example, like equatorial orbits in the xy plane, basically exactly the same example that we saw at the blackboard for the binary emission. In Cartesian coordinates, you find that the tidal tensor has these components. This is for a system on equatorial orbits. And if you plug these inside our expression there, are the Cartesian coordinates in x, so if you take an x, y, zeta coordinate systems and you are assuming that your system is on the x, y, that those are the coordinates. You can define a tidal Newtonian tensor, which is, sorry, potential. So that's the tidal tensor, and then if you plug that expression in our expansion from for phi, that expression will percolate here. So basically, if you expand as we did the Newtonian potential, you see that you encounter the Newtonian tidal potential, which is this object here. Now, you may ask how we generalize. This is basically all known since, I would say, after Newton. So this is all classical. And you may ask how to generalize that thing in a relativistic setup. And what we want to do is, in some part, the same as we have done with gravitational waves. So we want to study the tidal forces acting on a body. Okay, so I want to see how this body responds, how this body answers to an external tidal field. And what we're going to do is perturb this body again, as we have done in the for gravitational wave emission. For us now, the background will not be anymore like the flat space-time, but this, at the practical level, will be the neutron star or a star. Can be a black hole, but that will give some very weird result. Not very weird, but some different result. And this is the perturbation that will be sourced by the tidal field. When you know this, you know everything, and then you can also compute the effects on the relative acceleration between bodies, and you solve for the full system. Now, what we're going to do is all these formulas that we're going to develop is valid for spherically symmetric static combat objects. And assuming a stationary tidal field. Now, the first one is a statement on the object that I'm perturbing. I'm assuming that it's static, not rotating, and that it's spherically symmetric. You can relax the assumption of being rotating. It becomes way, way more messy, but I mean the approach and the technology that you can use to compute perturbation on a rotating background is exactly the same. Way more involved, but it's the same. Stationary tidal field. I'm actually here assuming that my tidal field, that source the deformation, is constant, okay? It doesn't depend on time, okay? Now, this situation is something that you may expect happening in the binary evolution of two stars, for example, two neutron stars. You expect that you have two non-rotating neutron stars, or two neutron stars which are rotating, or very little rotation. They are very practically spherically symmetric. They evolve, and because of the tidal field, they actually develop like some non-spherically shaped because of the tidal deformation. Now, something that would surely not be something that this particular physical situation doesn't describe is a stationary tidal field, because you may expect that during the binary evolution, the tidal forces become stronger and stronger as the object get closer. Okay, when they're very, very far, they barely feel the attraction. Okay, so you don't feel the inhomogeneity of the tidal field. But when they become closer and closer, they will be stretched more and more, which basically means that the tidal field is changing in time. So can we actually apply this formalism during our case, so for binary evolution? And you can, if you realize that there are different time scales at the evolution, at playing here, and as long as this time scale, they don't talk each other, you can actually work out all the mathematics, all the maths that we're gonna do, assuming stationary tidal field. And this is because there are two time scale. So the time scale of the tidal field, which is time scale on which the tidal field varies. And then there is the time scale of the deformation, which is the time scale on which the object responds to the deformation. Responds to the Now, if you assume that T def is much smaller than T tidal, basically your game will be that of a stationary tidal field. So you see what I'm doing here. I'm actually, I have like the tidal field which is acting on the bodies. Okay, take a single body in the binary. This body is being deformed by the external tidal field, and being deformed basically means that changes shape. But if the change in the shape is very, very fast, and is actually faster than the variation of the tidal field, then basically, so the star basically readjusts very, very quickly to the effect of the tidal field, then in this time scale, the tidal field will actually look stationary, so constant. Now, of course, this is called a diabatic approximation for the tidal field. Which basically has the same name of the adiabatic approximation that we use for the gravitational wave emission, but it has exactly the same meaning. So in the adiabatic approximation for the gravitational wave emission that we saw yesterday, we assume that the binary was jumping from an orbit to an orbit, but yet at the time to readjust to a circular configuration. So nothing super violent was happening, and it wasn't going from a circular to a radial or a very eccentric configuration. Okay, so as this is something that you would expect from very far spiral far from the merger, and this actually gave validity to our approximation. Here we're doing exactly the same. So I'm assuming that the star moves between different states, but these transformation, these changes are not too violent, okay, and such that the tidal field can be actually considered constant, and so you can work out basically a stationary field approximation. again, as for the gravitational wave emission assumption, you would expect that this doesn't really hold when you get too close, because at that case, the tidal field will become stronger, the deformation will actually, so the variation, the time scale of the tidal field, then it will become so fast that can be comparable with the deformation. So all of these need to be augmented with something else that, again, is numerical relativity. Okay? Okay, if you do this, in this setup, which is the standard setup that we use to compute the log numbers and the tidal deformabilities, so what we assume is that I'm going to use some terminology that, I mean, probably you ever, I don't know if you ever heard, but the induced multiple moments of the object are linearly proportional to the external field. So again, just to talk about nomenclature, I have the tidal field. This tidal field is deforming my object, so is inducing a non-trivial set of multiple moments. Okay, quadrupole, octupole, hexadecapole, I don't know what's the other, okay? So an infinite series of, if you take the gravitational potential and you expand these in Legendre polynomials, it has like a structures which highlights the different multiple moments of a compact objects. They did, for example, for the Earth, in order to understand that, of course, it wasn't like a sphere, but not even an ellipsoid. It was like a, I don't remember which is the technical name, but something with a lot of multiple different from zero, with characterize completely its structure. Okay, now here it's the same. I have the tidal field, which is inducing these quadruple, octuple, blah, 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 multiple moments. What I'm assuming, thanks to this setup here, is that the induced moments are proportionally, linearly, to the external tidal field. So, that basically this relation hold. So what this relation tell you? We actually have seen this already at the first, in one of the very first slides that I presented you. So these, let's take for now, let's look only at this part here of the blackboard. These are the mass induced moments. And these are the tidal moments. Actually, let me call it the electric tidal moments. Look only at this. These are the standard way, these are the standard things that you would expect happening in Newtonian gravity. You have a cascade of multiple moments. This capital L, just it's a very compact way to introduce a multipolar index. So this L just means it's a series of indices, actually, which with abuse of notation is called L1, Ln. For example, I know that it can be a bit confusing at the beginning, but there's nothing particularly fancy. So there will be different multiple moments given in terms of an index that I'm calling L. Okay, the L equal 2, so when L equal 2, that thing there will become Q. There are two indices, so there will be Qij equal to lambda 2 Gij. This corresponds to L equal 2 are quadrupolar deformation, so the things that deforms your spherical object into an ellipsoid. Okay? If you have L equal 3, you'll have Qijk equal L3 Gij. And then you can compute all the other things. Okay? This is the octuple, and blah, blah, blah. This is the thing that we have seen in the blackboard, and on the slides in the first lecture. So this is the mass quadruple, which, sourced by the tidal field, induced a tidal deformability, which is proportional to the log number. This is lambda 2 is 2, 3, K2, R25. This is something that we've seen at the very first lecture. So this tidal deformability is proportional to the log number and the radius of the deformed object. And this is the constant of proportionality between the tidal field and the quadrupolar field. Okay? This basically, roughly speaking, corresponds to the tidal tensor that we have seen before. If you, in the Newtonian version, you would have considered higher order moments, so you can actually develop all the technology that we have done for the Newtonian gravity, including higher derivative in R. If you remember, we basically stop at the second derivative. But if you consider higher derivatives, so third derivative of Newtonian potential, you will hit this guy here. So you have different multiple moments which will source different, you will have different tidal moments which source octuple, hexadecapole, and blah, blah, blah. Now, for us, we're going to focus just on this guy. And this is because it's the dominant contribution in general. So the quadrupolar deformation will be the largest induced, at least in the comfortable situation that we are studying. All the other will be extra deformation on top of the quadrupolar one. And also because d lambda 2 is the parameter that enters at the leading order in the waveform. So the waveform basically has this 5pn V10 over C10 factor, which is proportional to lambda 2. Okay? You can, of course, include and basically give a lot of work to do to a post-Newtonian guy, to add even lambda 3 and whatever. But this moment will be at plus n. So will be a higher post-Newtonian order. So what I'm saying is that at the leading contribution in the tidal phase, the quadrupolar log number will enter. The other octupolar, blah, 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 will actually enter at V11, 12, I don't remember exactly the order, but at higher order. And they will be all, the lambda 3 will be smaller than the lambda 2. So smaller deformation, at higher post-Newtonian order. I think for the sake of the lecture, we can just avoid discussing about it. Okay? The funny thing is this guy here. So this has a Newtonian counterpart, okay? So in the sense that actually, yeah, indeed, let me write the blackboard. As I was telling you, the capital G there resonate with the tidal tensor that we have written before, and then you can actually go along with the multipolar, and if you compute higher order derivative of Newtonian potential, you'll get like the Newtonian version of Gij, Gijkm, and blah, blah, blah. And indeed, we already seen it, but the quadruple of a max distribution is just this. I'm actually writing this in a compact form. The Newtonian version of this is this. Standard quadruple. I'm writing this in a super compact form, but this XL means XJ, XI, XJ, just written in a more compact form as R square, where and don't let me write this, but you recognize what it is, right? This is the second derivative of the potential, which is the tidal tensor. This is exactly dA dj of phi. This is proportional to di dj of phi, and phi is the Newtonian potential, okay? So this has an immediate, really, analog in Newtonian gravity with the things that we have seen before, okay? The only difference, besides not even the names of the tidal fields that you find in literature, is just that for sake of calculation, you need to introduce like this is a traceless version of the quadrupole moment, but modulo this compactified version is exactly the same as what we've seen before. Quadrupole moment and second derivative of the Newtonian potential. What you don't have in Newtonian gravity is this. This doesn't have any counterpart. And I'll write it again, so I have more space. This SL these are the magnet, well, see. Actually, no, sorry. Are the I'm not really eager to, I mean, you don't have to learn the names. This is just nomenclature that I guess you will forget after this hour, which is not really important. The real probably message here is that here you have another set of multiple moments, which are called the current multiple moments, which are induced by another GR general relativity component of the tidal forces. These are exactly, the indices here are exactly same as the first one. And the coupling between the two is given by what I call like magnetic tidal love numbers, which are different from the mass tidal love numbers. Now, where do these things come from? They come from velocity field deformation of the object. So the problem is that in general relativity, velocity per se gravitates, so induces a tidal field that can induce deformation. In Newtonian gravity, only mass gravitates, not even a spin, okay? So you don't see anything else than the mass quadrupole. In general relativity, all form of energy gravitate, this is the very essence. So, like velocity deformation will be associated to a set of tidal deformability L of numbers, which are called magnetic or current or odd tidal moments. There is a meaning why these things are called this way, but I don't want to enter. I just want to tell you that the very difference is that thing there is associated to mass moment, and that they have a Newtonian counterpart. This thing here, they are associated to velocity deformation, and they don't have a Newtonian counterpart. All the group of this term will be subdominant to the L equal to lambda 2. So you have lambda 2, and we have seen that lambda 3, lambda 4, and blah, 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 they'll always be smaller than lambda 2, so we don't care. But also sigma 2, sigma 3, sigma 4, sorry, the wrong sign. Also sigma 2, sigma 3, sigma 4 will be way smaller than lambda 2. So this magnetic tidal deformability induced by velocity deformation will be all smaller than the leading term mass component. Like this one, they will also enter a higher post-Newtonian order in the waveform. So they're okay if you want to publish a paper and say the relevance of this, but for us they're not really interesting, okay? The only thing that we're gonna care is this guy here. I think this is what current distribution. Yeah, current. Okay. The last thing is that we can associate. We call like this lambda tilde, this lambda and sigma as tidal deformability, which are connected to the love numbers, and the love number of the order L is given by this object. So for each of the lambda L, so for each of these, you can define a love number, which is also connect to the neutron star radius. And if you plug here L equal 2, you're going to find exactly what we've written at the blackboard, that lambda is 2/3 K2 R25, lambda 2. And then you can define the higher order moments with L equal 3 and blah, blah, blah. And the same with what we call the magnetic, so the sigma tidal deformability, that are connected to this. I hope that this is correct. Should be this. Which are the magnetic love numbers. Yes? Double factorial. Yeah. Okay. Now, how we do compute lambda and k? It's an operation on the, I don't remember exactly. It doesn't go too much from n times n minus 1 times n minus 2. And I use mathematical in general too. It's an algebraic operation on real numbers. Okay. The last thing that I want to mention today is that how do you compute the tidal love numbers? There is a procedure to do this. The basic procedure starts with what I've described before. So you take a neutron star, you perturb it. This perturbation encodes the property of the tidal fields. You try to see how the star responds, and in particular, how this star develops the quadrupole moments that associate to lambda 2. Now, there is a very little subtle, is that where do you measure the quadrupole moment of a neutron star? It's a very, very ambiguous definition, also because you could have actually asked me the same question in general for gravitational wave, because it's super difficult to disentangle in GR the quadrupole moment from the background metric. For the simple fact that you never measured the background and the perturbation. What you get at the end out of it is a surrogate of the two, and boom, what is the two? So, the game in general that you have to play in this is that you have a star, which is spherical. The tidal field will induce a deformation with a quadrupole moment. What we're going to do is study the perturbation and see basically the solution to g mu nu equal to g mu nu 0 plus h mu nu. And this encodes the deformation between these and these sourced by the tidal field. We will compute this solution up to here, but this won't be enough, because up to this point, I'm still not able to basically to disentangle these two. The way to disentangle two is to match this solution at infinity with an asymptotically flat description of the spacetime from which you can unambiguously read the multiple moments of a compact object. I see you a bit perturbed. But what we're gonna do, let me write the equation, probably is easier. So again, we're gonna compute the metric tensor, the full solution. Then we're gonna expand this metric tensor at infinity for large spatial R, and in particular we will compute this in a Cartesian mass-centered frame in which for example, the GTT component of the metric there is an asymptotic here, asymptotic, such that this metric is HCMC, asymptotic Cartesian mass-centered frame, in which this has this form. If you understand this, I can live today, I'll be happy, to be honest. Also because it took a while for me as well to understand. Probably I don't understand this as well completely, but. So you see, in this metric here, this is a metric that describes an asymptotically flat spacetime, so something which resembles very much Minkowski metric. You can write this, you can write the GTI and GIJ components, and they will always be, the GTI will be 0 plus something, the GIJ will be delta I, so 1 plus something. So it resembles something which is the Minkowski metric, but has deviation in 1 over R, so it's the asymptotically mass frame. For a spherical symmetric distribution, indeed, you only see this. But for a generic orbit, generic object with multiple moments, it provides an unambiguous gauge invariant definition of the multiple moments of the source and of the source of the deformation. These, I didn't include terms larger than 2, but you see, sorry, this is a 3, that this metric, which for a spherically symmetric compact object will only have the Schwarzschild-like term, contains a 1 over R3 contribution which is proportional to the mass-induced quadruple moment. So, fuck, I cancel all the necessary things. So it contains this. And then it has a growing solution which contains the source of the deformation, so the tidal field. Now, this metric here is gauge invariant, is written in asymptotically, so it approaches the Flat's metric, and here the definition of the multiple moments is not ambiguous. So not ambiguous means that you can easily see what is flat spacetime, what is the background, and what are the parameters that define the star structure. So what's the game? The game again is take this solution that can be only computed numerically because we have to solve it inside the star. Get the solution at the boundary where there's vacuum. We're going to do this end by end, but step by step. Then expand this solution at infinity and match this solution. So we'll have a G mu nu, let me call it numerical, expanded at R goes to infinity, and match this solution with this form here. Then, from this piece, you recognize that there is a decaying solution, this is super important, and a growing solution. The decaying solution is associated to the quadruple tensor. The growing solution is associated to the tidal tensor. What you do is that you match this with this. You identify in this which is the solution which is decaying. You identify with this the solution which is growing. You associate these two. You solve two algebraic equations, and you find Q and G. And once you find Q and G, you take the ratio and you compute the log number, or the tidal deformability. This is basically everything. Absolutely, but I mean, it diverges, but this is not a compact object. This is not a black hole which is asymptotically flat. It's a compact object with a tidal field. No, the tidal field will actually fall off at some point. The tidal field will have a fall off. The GIJ has a fall off. Yeah, yeah. Yeah, absolutely. Depends on the yes. It does, and the Newtonian version decays as 1 over r cubic. Sorry, say it again. Yeah. Yes. No, but this is dictated. The problem is that this is dictated, this is fixed. What I'm actually matching is a solution of the source. No, of course, wait a second. So these are constant numbers actually. Because these are a specific, yeah. I mean, yeah, if you wish, I mean, if you add that term there, the matrix diverges as r squared, yeah. No, this is wait a second. This is not the field of the neutrons. This is the field of the tidal object. Of the sorry of the this is not the response of the star. This is the thing generated, for example, by the companion object. GTT, sorry, say again. Yeah, this is something. So this is something that you would measure. This is the observer thing. Let me think for a second. I'll give you the. But yeah, so the point is that in principle, you have to do this. You have to match the two solutions. No, it's a good point. Let me think for a second out of this, and hopefully I'll give you the answer. No, nothing. No, the other thing that I want to tell you, but we're not going to use it, is that if you want to compute the sigma, which we won't do it, you can find basically, you can have to match it to the GTI of this, and this will contain information on the S and on the H, and so exactly like this. And I think that the funny thing is that at the linear order, so the dominant term, I won't write all of this. So the GTI actually depends on this J, okay. I, J, K, J of J, and these are the components of the angular moment of the object. So for us, this will be 0 because we are considering a static background, so which is not rotating. But if you wanted to compute the perturbation of a spherical object, you also have to consider if you want to compute perturbation of a rotating star, you also had basically to compute all the matching, including this term here. Nothing about this is the mass of the object. I think that's it. We can tomorrow. What we're gonna do is we're gonna forget about this matching because this only comes at the end of the perturbation, and we're gonna compute this for a perfect fluid which describes a neutron star, and we're gonna see how the components of the metric tensor there up to a certain point because the solution will be fully numerical, and then we're gonna develop the perturbations. Oh. Sorry? Yeah, it depends on R. Now let me think about this of the full matching procedure. Yeah, it depends on R. It still confused me for a second because it contains an extra dependence there. So let me think for a second, sit, and then I'll give you the answer. Okay, lunchtime.